Hello, welcome back. In the previous module, we learned about the BigM method, which helped us in overcoming the modifications given to the original problem and also helped us in getting the solutions of the original problem from the modified problem. The two-phase method is an alternative to the BigM method in which the solution is carried out in two phases, where in the first phase we attempt to find the starting basic feasible solution by minimizing the sum of the artificial variables, and in the second phase we use this starting basic feasible solution for the given objective function and solve the original problem. To illustrate the two-phase method, we shall consider the linear programming problem that we have used in understanding the BigM technique. That is, minimize z is equal to 4x plus y subject to the constraints 3x plus y is equal to 3, 4x plus 3y greater than or equal to 6, x plus 2y less than or equal to 4, x and y greater than or equal to 0. Let us rewrite this problem as maximize z prime is equal to minus 4x minus y subject to the constraints 3x plus y is equal to 3, 4x plus 3y greater than or equal to 6, x plus 2y less than or equal to 4, x and y greater than or equal to 0. In order to use the simplex method, definitely we need a standard form, and hence we have maximize z prime is equal to minus 4x minus y plus 0s1 plus 0s2 plus 0a1 plus 0a2 subject to the constraints 3x plus 1y plus 0s1 plus 0s2 plus 1a1 plus 0a2 is equal to 3. 4x plus 3y minus 1s1 plus 0s2 plus 0a1 plus 1a2 is equal to 6. 1x plus 2y plus 0s1 plus 1s2 plus 0a1 plus 0a2 is equal to 4, where the variables x, y, s1, s2, a1, a2 are all greater than or equal to 0. In this form of the linear programming problem, because of the introduction of the artificial variables, the original maximization linear programming problem got modified into another maximization linear programming problem. As we did so in the case of BigM method, here no correction mechanism is introduced in the objective function. So, from here we have to deviate into an alternative method to the BigM method called the two-phase method. Here we solve the problem into two phases. Consider the phase 1 problem shown here. Minimize s is equal to a1 plus a2 or maximize s prime is equal to minus a1 minus a2 subject to the constraints 3x plus 1y plus 0s1 plus 0s2 plus 1a1 plus 0a2 is equal to 3. 4x plus 3y minus 1s1 plus 0s2 plus 0a1 plus 1a2 is equal to 6, 1x plus 2y plus 0s1 plus 1s2 plus 0a1 plus 0a2 is equal to 4, where all the variables x, y, s1, s2, a1, a2 are all greater than or equal to 0. The objective of this phase is to always minimize the sum of the artificial variables subject to the same set of constraints, that is, minimize s is equal to a1 plus a2, or equivalently maximize s prime is equal to minus a1 minus a2. Hence, let us solve this phase 1 problem shown here. Maximize s prime is equal to 0x plus 0y plus 0s1 plus 0s2 minus 1a1 minus 1a2 subject to the constraints 3x plus 1y plus 0s1 plus 0s2 plus 1a1 plus 0a2 is equal to 3. 4x plus 3y minus 1s1 plus 0s2 plus 0a1 plus 1a2 is equal to 6. 1x plus 2y plus 0s1 plus 1s2 plus 0a1 plus 0a2 is equal to 4, where x, y, s1, s2, a1, a2 greater than or equal to 0. The initial simplex table or the first simplex table for the phase 1 problem is shown here. The second simplex table of the phase 1 problem is also shown here. The third simplex table for the phase 1 problem is shown here. The third simplex table is the optimum table, as the NER values are either positive or 0 only. Hence, x is equal to 0.6, y is equal to 1.2 gives the maximum s prime is equal to 0. We also have x is equal to 0.6, y is equal to 1.2 giving minimum s is equal to 0. For if this minimum value of the phase 1 is positive, then the given linear programming problem does not have the feasible solution. Since minimum s is 0, we can proceed to phase 2 to find the solution of the given maximization linear programming problem. To enter into phase 2, first delete the columns of the artificial variables and get a new table. That is, we get the simplex table. Writing the entries of the table in the LPP form, we get maximize z prime is equal to minus 4x minus 1y plus 0s1 plus 0s2 subject to the constraints 1x plus 0y plus 0.2s1 plus 0s2 is equal to 0.6, 0x plus 1y minus 0.6s1 plus 0s2 is equal to 1.2, 0x plus 0y plus 1s1 plus 1s2 is equal to 1, where the variables x, y, s1, s2 are all greater than or equal to 0. This problem is equivalent to the original problem and is referred to as the starting basic solution of the phase 2 problem. Since minus 0.2 is the most negative NER among the NER values, S1 is the entering variable. From the minimum ratio 1, we find that S2 is the leaving variable, and this gives 1 in the intersection of the S2 row and S1 column as the pivot element. Therefore, applying the row transformations in order to shift the basis of the leaving variable to the entering variable, we get the second simplex table of phase 2. As the NER values are non-negative, this table is the optimum table. Hence, x takes the value 0.4, y takes the value 1.8, and the maximum of z prime is equal to minus 3.4, or equivalently, x is equal to 0.4, y is equal to 1.8, and the minimum of z is equal to 3.4. The choice of the huge value m in the big M method can lead to round off error and hence will affect the accuracy of the solution. But this two-phase method does not use such a huge m, and as a result it is more reliable method than a big M method. Thus, so far we have seen all the basic techniques required to solve a linear programming problem by simplex method. In the next video, we shall learn about the transportation problem and methods of solving the same. Thank you.